Now get PowerPoint open again from current slide. Okay. Comment is here. All right, good deal. All right, say it again. I'm running a little late today because of an issue at Kirkland Clinic that was not resolved. I had to sit there most of the morning. We just started getting started now. That's why we're late doing it. But the other thing is, yesterday afternoon, I could not access the test bank, so I could not get your test ready for today. So I hope to be able to get it resolved today. If I can find, if it's resolvable, I hope it is. I'll have to call the customer service or whatever they do. I called last night, but of course they are closed long before I called. So they're on Eastern time, and I called Central, and they weren't there. Okay. Any questions on anything we've covered so far? We're on the very last section in Chapter 3, a long chapter. Okay? And we're talking about differentials. Any questions? Like I said, I'll try to have your test ready Monday. I wanted to have it today so you can work on it on the weekend. Okay, we talked last time about the tangent line to a graph of some function f at the point C, which is obviously on that function, and alpha c is the x value. Alpha c, of course, would be the y value. The equation for the tangent line, since alpha c is a point, then y minus alpha c is equal to the slope, which is f prime of c. Okay. Now, of course, f has to be a differentiable function at c. That's understood. So f prime of c is going to be the slope, and x prime of c is that. Add the f of c to both sides, and you get this. Okay. This tangent line is used as an approximation of the graph of f. The quantity x minus c is called the change in x, which we always have called it delta x, okay, as shown here. So, here's your x minus c here. If you're at some value of x other than c, and they seem to indicate this is the value where you are, then this is your x. And I didn't list it this way, but this is your x. X minus c would be this distance. And x minus c is delta x. Okay? Now, it sounds like we're going around our elbow to get to our ear, and we kind of are. But if you pick up on this, down here, well, let me get my pen activated. I hope this isn't more confusing than it's worth. Okay, here is your x. I don't know why. Okay, there is your x, and the x is equal to c plus delta x. Okay? Okay, and that came from the fact that x minus c was equal to delta x. So if you add c to both sides, you get x equal c plus delta x. So that's how this became your x. Okay? Now, that's what they've shown so far. When this delta x is small, in other words, this is fairly close to your c, okay? When this delta x is pretty small, you get a very good approximation here between the tangent line and the function itself. The further out you get, the more it deviates, okay? But it's a very good approximation close in. When delta x is small, the f of c plus delta x, okay? Here's f of c plus delta x up here, okay? Minus f of c, okay? That's that, okay? That's approximately F prime of C times delta X. So F prime of C times delta X is the difference here. That is how much the function's increased here. This is how much it really increased. This difference tends to be pretty small. That's what they're getting at. They've got so many deltas in there and other things going on, it's sometimes a little baffling to follow what they're talking about. Okay? So, but as long as the delta X is fairly small, this is a pretty big one here, so you have a little bit of error there. But if you're down in this range, delta X being only like this, then you're really, really close to what that function value is. Okay? Now, why are we talking about this ad nauseum? Okay? When delta X is small, the change in Y, denoted by delta Y, can be approximated. And this isn't what it is, but approximated as F of C plus delta X. Now that's your F of X minus F of C. That is, let's go back to the picture here. Here's F of C plus delta X is this value here, and this is, still don't show this very well, F of C, so, here it is. Here's the F of C right there, and F of C plus delta X is there. So this is the difference between when you went over delta X here, how much this changed, okay? Your tangent line accounts for this much of that change, and you're just left with a little bit more of it, okay? So that's what you're getting at here. The delta Y is your F plus C minus F of that. That's what the actual change of the Y is from C to X, which is C plus delta X. And that's approximately equal to F prime of C delta X. So what they're saying, going back here again, this is the actual difference when you go from F of C to F of X, which is C plus delta X. You're making a change of here on your actual function values, okay? Now, as long as the delta X is very small, that's not far off from what F prime of C is. Here's your F prime of C. There is a little difference there, but it's not a lot. This is a good approximation of that. Not great, but good. If you go down here, your delta X is smaller and smaller, then it gets to be a better and better approximation. Till right in here, you can hardly tell the difference, okay? That's what they're getting at, okay? So that's approximately F prime of C times delta X. For such an approximation, the quantity delta X is traditionally denoted by dx, meaning it's approaching 0, and it's called the differential of X. So the expression F prime dx is denoted by dy, and it's called the differential of Y. Okay? All this, the graphics and everything else, trying to get you to see this. Okay? Here's your definition of differentials. Let Y equal F of X, right? Good. You got it. Represent a function that is differentiable on an open interval containing X. Everywhere in that X there is differential. The differential of X, dx, is any non-zero real number. So it can't actually be 0, but it can be very close to 0. The differential of Y, denoted by dy, is this, and it's F prime of X dx. Okay. All that to get you there. Okay? Aren't you glad we took all that time to get there? Now let me show you what to me is a pretty easy way to think of it. Okay. F prime of X. What's another way to write that? Say in Leibniz notation. Yeah. Isn't that the same as dy or df? Let's see. Yeah, let's do dy. dy dx. Okay? Isn't that how we often write your derivative? I've got it so ugly in there. Okay, let me clean this up a little bit. Okay. Now, this is not what we're doing. Mathematicians would roll over in the grave if they thought I was suggesting this. Okay? Even if they weren't dead, they'd be rolling over in the grave. What happens if you... Okay, you're not doing this, so don't get me wrong, but multiply both sides of the equation by dx. What would you have? dy is equal to f prime of x dx. Wait a minute! That's what we just said down here. Now, that's not what we're doing, but that's, in essence, what we're talking about here. You still got delta x's, delta y's, they're becoming dx and dy, and basically, that's what a differential is. You just rewrite it as dy is equal to f of x dx. Differential is not the same as a derivative, but they're very, very closely related. In many types of applications, the differential of y can be used as an approximation of the change in y. Okay? So that delta y is approximately dy. Okay? Or delta y instead of dy is approximately f of x, f prime of x dx. Why didn't they put a delta x there? I'm not really sure, but they left the dx there. And that gives how much the y has changed over a small change of x. That's exactly what derivatives tell you, okay? So basically, this is just, it's not playing around with the notation. Now, here's why you can't multiply. This is not a division. This is an operator, dy dx. That's f prime of x. So you can't multiply by dx. But if you want to think of it that way, what's the hurt? Okay? Because that's exactly what you get. Because all, huh?
What do you mean it's an operator?
Dy dx is taking a derivative. It's not dy divided by dx. Okay? It's just an operator. But this notation is suggesting it can almost be treated like that, which is exactly what you're doing. Where did the dy dx come from anyway? Change of y over change of x. So delta y over delta x, you let delta x approach 0, but not get to 0, it becomes a dx, and your numerator becomes a dy. Well, you're just doing this in a different context, but you're still doing that same type thing. Okay? Now, the reason we're doing this is that this leads to integration, which is our next topic. So, let's let y equal x squared. A good differentiable function everywhere, right? Find dy when x is equal to 1 and dx is equal to 0.01. Okay? So what you reckon we're going to have to do? What do you reckon we're going to have to do? Take a derivative, I wondered when someone was going to say it. So how do you want to write that? You want to write it as y prime rather than dy dx? Because we're going to be using dy's and dx's. I don't know if you find that helpful. Y prime is equal to what? 2x. Perfect. Okay? Now, find dy. Now, what did we just say dy was? dy is equal to, help me with it, f prime of x dx. Okay? Now, they tell you when x is equal to 1. So when x is equal to 1, f prime of x, okay, is equal to, and that's the same as y prime. So, oops, when that's equal to 1, x equal to 1, this is equal to 2. Okay, right? So it would be 2 dx. Well, what's your dx? 0.01, right? So your dy would be dy equal 0.02. Okay? Now, it says compare that value with the delta y for x equal 1 and delta x equal 0.01. Okay? Well, what they want you to do there is think of it this way. Think of y of 1 or f of 1, whichever way you want to think of it. What would that be? 1. 1 squared is 1. Okay? And then think of it when your delta x, so y of 1 plus 0.01, which would be y of 1.01 is 1.01 squared, right? And what does that give you? You can use a calculator if you want to. You might be able to do it in your head. 1.01 squared. $1.0201. Is that what you said? Okay. So now you have y of 1 and y of 1 plus L. So the change of y would be 1.0201 minus 1, which is 0.0201. So your dy here was that, your delta y was that. I'd say they're pretty close, wouldn't you? Close enough for government work. Okay? This is your kind of like your approximation. That's the actual change of your y. Pretty close. As long as the delta x, in this case dx or delta x, 0.01. That's pretty small. Okay? As long as that's small, your approximation is going to be pretty good. Okay, that's how we did it. Let's see if they do anything any differently. Maybe it's clearer. Let's see. Because y is equal to f of x, which is x squared. You have f prime of x, 2x, exactly what you did. The differential dy would be dy is equal to f of x dx. So that would be f of 1, f prime of 1, which would be 2 times 0.01, which would be 0.02. Exactly like you did, that was your dy. Okay? Now, using delta x equal 0.01, the change of y would be f of x plus delta, which would be f of, excuse me, I got the hiccups. The change of y, f of x plus delta x minus f of x. Yeah, that was your numerator on your derivative, remember? Okay? That's f of 1.01 minus f of 1. And y'all just calculated that for me to be 1.0201 minus 1 is 0.0201. So whereas your dy was this, your delta y was this. Okay? Really close. Within 1%. Okay? Pretty close. Actually, less than 1%. Okay. Now here's example 2. Comparing delta y and dy. And folks, we're going to do all this, and I have yet to think of a very practical reason we're doing it. I mean, I know theoretically why we're doing it. We want to see that this is going to work when we do integration. It's close enough, you know. But this itself, not a lot of places. I mean, I can imagine some places you might want to estimate. But let's see. Okay. Example 2 was let y equal x squared again. Okay, just like the first. Wait a minute. Earlier wasn't an example, it was just, I'm getting confused now. This looks like what we just did. And I thought we were doing the example. Let me go back and just remind myself. Oh, okay. No, this was example 2. Sorry about that. Okay. This is what we were just doing. And because we did all that, and then they show the figures. So that's all the difference here is. Okay, here's the point x, when f of 1, when y is equal to x squared, plug in f of 1, x equal 1, and you get y is equal 1. So here you are at 1, 1. When you go over just 0.01, that's not very far, okay? But they've blown up the scale here really, really big. This is 0.01. 1 would be somewhere way, 0 would be somewhere way over there. 100 times further than that. Way, way over there. So they really have blown this up. Okay? The change in y, which is your delta y, is between here and here. Okay? That's what the 0.0201 was. Whereas your dy was this part here, which is 0.02, is the difference between those two. Okay? And this line is 2x plus 1, because your derivative at 1 was 2, and x minus 1, there's your 1 down here. So this is that line. And you plug in x equal 1.01, and you'll get the same answer we just did. So I don't know why they're showing it over and over again, but you're estimating this difference by that difference. And it's a pretty good estimation in all terms. The difference here was 0.0001. Okay, so that's pretty close. Okay. So I feel like they've beaten it to death. They do show a table here. And the table is pretty instructive as well, and maybe even more instructive than the figure just was. I'm surprised they didn't do this on the slide as well. But you see, when you're at 1, you're exactly on. 1.01, that's the one we just did. The f of x was 1.0201. The y from your derivative estimation, linear approximation, 1.02. Not far off. When you go to 1.1, that's 10 times as far away as you did 1.01. You're still at 1.21 as opposed to 1.2. Still pretty close, okay? When you get up to 0.5, though, you now are off by, so in the first place, you're good to the nearest 4 significant digits, okay? Then you go down to 2 significant digits, and then you're only down to 1 significant digit. So the further away you get, the worse the approximation is, which should not be surprising. And you can go the other way and see the same result, okay? Any questions? All right, now we're going to talk about error propagation, okay? If you let x represent the measured value of the variable, and x plus delta x will then be the exact value, okay? Then delta x is the error in the measurement, okay? Now, what are we talking about here? You've got some sort of a device, okay? And you want this device to be 3.00 micron, 001 microns, something like that, really small. And your actual measurement is, okay, the measured value is 3 microns, but the actual measurement, exact value, is 3.01 microns, okay? Not a lot of difference, but delta x is the error in that measurement, okay? So finally, if the measured value, x, is used to compute another value, f of x, then the difference between alpha of x plus delta x, the actual value, and the alpha of x is the propagated error, which is exactly what we were talking about. So your alpha of x plus delta x, the exact value, minus alpha of x, the measured value, the propagated error is the delta y, the difference between those two. Okay? Now, let me just say this, apart from the math part of it, errors grow, okay? They really do, especially in certain situations. Every now and then they will cancel each other out, but that's when you're very lucky. But in general, errors grow. The more operations you do on an approximated value, the further you can get from the truth, okay? So that's why I would say this. So the measure, this is example 3, top of page, or sort of middle-ish of page 237. The measured radius of a ball, which is really ridiculous, okay? The measured radius of a ball bearing is 0.7 inch, okay? Why is that ridiculous? Why did I just say that? The measured radius of a ball bearing. You can't measure the radius. What they're measuring here is what? The diameter. It's impossible to know exactly where the center is and to measure the radius. So they should be saying the measured diameter of a ball, and then take half of that and calculate the radius. Okay, I'm being picky, but that's ridiculous. The measurement is correct within 0.01 inches. Okay, estimate, the propagated error in the volume V of the ball bearing. Okay. 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 All right. Well, let's go back and remind ourselves of the formula we'll be using. The delta y is the propagated error. So I'm going to write that in front there. Delta y is equal to alpha of x plus delta x minus alpha of x. Okay? Now, the delta x is your 0.01. The x is the 0.7. So here's your x, and here's your delta x. Okay? And what we want to do is calculate the delta y. Okay? Now, you could do it brute force, like we just said, f of 0.71, okay? Rather than call it f, let's call it r, because I like to choose my my names to represent what it is. This is going to be the radius function, okay? R and R. So this is R. Nah, that's not quite right. Sorry. The function that we're dealing with, I'm sorry, the x is the radius. So rather than saying x, let's call it R. That's what we should be calling R. Okay? And there's Chaston. And Chaston, I told the others, as they've been coming in too, I tried to get your test made up last night. I could not access the test bank. So I knew you were looking forward to having it this weekend, and I'm so sorry I didn't give it to you. You're such kind people. Okay. Your change of V, change of Y, this is actually the volume. This is change of V, and that's your V of R plus delta R minus, okay, for some reason I did it again, okay. This is the volume function, okay, as a function of R minus V of R, okay. So let's change this to, I prefer to have things representing what I'm, what I'm wanting. The change of volume is that minus V of R. Now, what is your volume? I swear. Okay. I'll get it right in a minute. Okay. Maybe. Okay. 0.7. Your R was 0.7. So let me go back and change this to. Okay. This is R, and that's your delta R. Okay. Okay. The measured radius, R, is equal to 0.7. There it is. And your error in that, the measurement is correct within 0.01 inch. So that would be your change of R, your error in R. Okay? So your change of volume here, and now I'm wondering why I put Y here. So let me get all this changed. Okay. I know you have written it the way I wrote it the first time, and now you've got a mess on your hands. Okay. All right. This is the difference in those two volumes. What is the volume of a sphere if you know its radius? Anyone remember that? Volume of the sphere. Oh, my. I'm not even sure this book has those kind of things in it. Let me see. This just has integrations and all that kind of stuff. How about in the back? Goodness gracious. Yes, it does. Back inside cover of your book. Volume of a sphere. No one brought your book. Oh, some of you did. No, 4/3. 4/3 pi r cubed. Okay? So, this is 4/3 pi times 0.71 cubed minus 4/3 pi times 0.7 cubed. Well, the 4/3 pi can be pulled out front, 4/3 pi, and do the difference of 0.71 cubed minus 0.7 cubed. So that basically is all you need to do. What is 0.71 cubed? Anyone got a calculator? Second? 0.71 cubed. .357, blah, 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 okay. Minus, and what's 0.7 cubed? Okay, blah, blah, blah. If you got all those on there and take the difference of them with as many digits as you have, what does that become? It looks like something on the order of 0.017 or so. Do the actual, don't round off. 0.71 cubed minus 0.7 cubed. Get a difference. Got it? 0.71 cubed minus 0.7 cubed equal, then multiply by 4, by pi, and divide by 3. Okay. Be sure you, okay. If you want, okay. Don't use these numbers. Use this. Do it just like you see here. 4 divided by 3 times pi times, open parentheses, 0.71 cubed minus 0.7 cubed, close parentheses. Do it that way. Don't round anywhere in the process. See what you get. Okay, say that again.
0.0628.
Okay. All right. We'll let you round there. Okay. Now, see, the radius was good within 1/100th of an inch. Your volume is only going to be not even 1/600th of an inch. So your error propagated. It grew from 0.01 to 0.0628 or something like that. So you see error does grow generally when you're doing this. And they actually did all right. That was the actual, I thought that's what they're at. Oh, I'm sorry, I didn't read it well. It says estimate the propagated error. We actually calculated the propagated error. When you estimated it, you used the equation we did earlier. They don't even calculate it. I thought they were. Okay, this is the actual error here. I thought that was what the purpose of this thing was. So let's go back and do the estimated, okay, from what we did before. Now this time we're going to do the delta y, actually the dy, you know, delta r, you know, well, delta v, okay. They're actually going to do the dv, okay, so let's go and do the dv. dv is, remember what dv was? V prime dr, right? Got it? So, if your volume is equal to 4/3 pi r cubed, what is your V prime? Take a derivative. It's really not that hard, is it? It's what? It's 4 pi. 4 pi r squared. So you see you're doing 3 times 4/3, right? It's 4 pi, and then drop the r by 1 power r squared. Okay? Okay, so there's your V prime. Okay, so we're using this formula now, dv, not delta v. Okay? And your dr, we already know that to be 0.01. Okay? So your dv is equal to 4 pi 0.7 squared times 0.01. Okay. The math is a little bit easier here, right? Okay. This will be 4 pi times 0.49 times 0.01. Okay? And if you get your calculator out, because I can't multiply pi in my head, but 4 times pi times 0.49 times 0.01, what do you get? Four times pi times 0.49 times 0.01. Okay, a little slower. 0.06 what? 1, 5. Okay, yeah, they round it to 8 inches. Okay, now that's their cubic inches. Okay, because it's a volume measure. The estimated thing, and that's what they said, estimated propagated error, that's your dv rather than the delta v. The actual propagated error is this one, is this one. Still pretty close, really close, but notice how the error grew from 0.01 from your measured value to your calculated value, 0.06. But of course your volume is bigger too and everything else. So. Okay, and that's cubic inches. Now, Would you say the propagated error in example 3 is large or small? Well, it seems like a pretty small number, doesn't it? 0.06, that's pretty small. The answer is best given in relative terms by comparing the dV with the actual V. So your dV here is 0.6158 compared to your actual volume and that was your, we didn't actually do it, we combined it. Your actual volume was 4/3 pi times 0.7 cubed. Okay, so you'll have to do that calculation. 4/3 pi r cubed, so it'd be 4/3 times pi times 0.7 cubed. Wait, just a second. Okay, I was cleaning up my mess. 0.0. Okay, what was that?
1, 4, 3, 6, 8.
6 what? 8.
8.
Okay. And let's see. Okay. Okay. Now they did it much easier than we did. Sorry about that. I was having you go through it brute force. If you actually did it, okay, remember the V prime was 4 pi r squared dr divided by 4/3 pi r cubed. Without putting any values in, notice your pi's go away, the 4's go away, and all but one of the r's go away, and what you're left with is 3 dr over r. And then plug in 0.7, that'd be 3 times 0.01 over 0.7. See what you get there, if you get the same answer. Oh, wait, okay, sorry. We're doing apples and oranges here. You would need to do this division first, and then do that division and see what you get. I'll do the numerator for you, 0.03 divided by 0.7. .0428. That's what they got in the book. And if you wrote that in a percent, that would be 4.28%. Now, I've left off the plus or minuses because it could have been plus or minus. It says within 0.01 inches. So if you just did that, it's plus or minus this, or plus or minus that. So 4.28%. Not bad, but not great. I mean, if you're doing a lab here on campus, if you're within 15%, that's pretty good. But if you are manufacturing this for a company, they may not like a 4% error. They say, we want your error less than 1%. You know, then you got to get your error down much, much smaller. Okay. Now, my younger brother used to work when he first got out of college for a company. Remember the name, Reliant Electric, or that wasn't it, was something, electric motor company, and they built motors for clients, you know, but they tended to get away from Navy as a client because Navy specs were always far more less forgiving than the others. They wanted it to far closer precision. Because guess what? When you're out there at sea, you don't want things breaking down because, well, the ball bearing was just a little too big, you know. So he said Navy specs were awful. And when they bid on there, they had to charge a whole lot more because they were very, very low tolerance. Okay. Again, this is all really interesting stuff, isn't it? Okay, calculating differentials. Each of the, let's see if we can move on. Oh, here, we'll watch how they did it. The formula for the volume of a sphere is 4/3 pi r cubed, that y'all were scratching heads about, where r is the radius of the sphere. So you can write the r is 0.7, and the possible error, the delta r, I was saying 0.01, but it's plus or minus 0.01, between negative 0.01 and positive 0.01, okay? To approximate the propagated error in the volume, approximate the propagated error, we differentiate v to obtain dv dr using that v, 4 pi r squared. Now here's a strange little feature. Maybe it's not strange, but to me it's always amazing. That 4 pi r cubed, pi r squared, is exactly the surface area of the sphere. And why the derivative of the volume is the surface area, I haven't wrapped my head around, but that's exactly the surface area of the sphere. That's beside the point. Okay, so there's your dv dr, okay? And what your actual change is of volume is approximately your approximate value, your differential value, okay? Now, what we did the first time was the actual change of volume. I wasn't doing the approximate, I was doing the other. So this would be 4 pi r squared times your dr. In other words, your dv is 4 pi r squared dr. Now, you're not doing this, folks, but it sure looks like you did it. It looks like you multiplied both sides by dr. But that's not what you were doing. It just looks like that, right? Okay? But you can always do that, okay? That's how you get your dv. And then just plug in 4 pi 0.7 squared, and then it says plus or minus 0.01, which is sort of hard to do, but that would be, just bring the plus or minus out front, 0.06158, which is what y'all got, right? So the volume is propagated error about 0.06 cubic inches, okay? The ratio, though, dv over v, which would be your error, estimated error over the actual volume, using the formulas rather than having to plug all that stuff in, you get the 0.0429, which is exactly what that's the relative error, and then you multiply that by 100% and you get 4.29. And they really, if they're going to put plus or minus there, you should say plus or minus 4.29%. And if a company's happy with that, you're fine. If they wanted it less than 1%, you got a lot more precision to put into your problem. All right. Now we're calculating differentials as if we didn't realize we were, okay? Each of the differentiation rules can be written in differential form, okay? For u and v to be differentiable functions of x, the constant multiple, remember we used to say d by du of cu is c du. Well, it's c. You just multiply by du, okay? D of, okay. I guess a better way of saying this, if this was, differential of x. If this was d by dx of cu, that would be c times du dx. D by du of, d by dx of u plus or minus v would be du dx plus or minus dv dx. All you've done here is multiply through by your dx's, so you don't have the dx's anymore. You just have the thing. Your quotient rule, your product rule was d of uv was du was u prime v plus v prime. Yeah, same thing here. The only thing is you just leave off the dx, okay, in the denominator. U dv plus v du. Okay, which is sort of what we used to say, right? And the quotient rule, derivative of u divided by v, is low d high minus high d low over low low. It looks, these are exactly the same, except you don't have your denominators in there. You don't have the dx. It's just d's and dv's. Okay? So it makes for writing a lot simpler. Just remember, well, that's what you do. Okay. So here's the function. Y is equal to x squared. Derivative is dy dx is equal to 2x. Your differential is dy is equal to 2x dx. Okay? Now, I say you can think of multiplying by dx, but don't, you're not doing it, okay? But actually just do here. dy is equal to 2x dx. I mean, just do it there. That's the differential form. This is the derivative form. So that's the differential form of the derivative. They're almost identical. I mean, they're saying the same things. Okay? When we get to integration, that's what will be integrated. You don't integrate this, you integrate that. Okay? Oh. I don't know why they're doing the work for you. This is supposed to be an example. Okay? So I'm going to do it better this time. Okay? If that's your y is equal to square root of x, what would be the first thing you would do to take a derivative? Rewrite it. And what would you rewrite it as? No. That would be 1 over x. What would be your power?
1 over 2.
1/2. That's square root. Your numerator is the power of the variable, and your denominator is the index of the radical. So that would be 1/2. Okay? And what would be the derivative of that then?
1/2 x.
1/2 x to the
Negative 1. Negative 1/2.
negative 1/2. So it would be 1 over 2 square root of x, if you want to write it that way. And that's how they write it. Okay? Now, what do you think the differential would be of that? Okay? All you do here is dy is equal to, and again I'd rewrite it, 1/2. Okay, y is equal to 1/2. Y is equal to x to the 1/2. dy would then be 1/2 x to the minus 1/2, which would be exactly this. So dy would be dx over 2 times the square root of x. This part looks the same. It just looks like you've multiplied both sides by dx. But you don't have to even do this step. Just do. Let me write it down for you, because this one, they leave out too many steps. Y is equal to x to the 1/2. You do dy is equal to 1/2 x to the minus 1/2 dx. It's like a chain rule thing. Okay? You take the derivative of this and then the dx. The differential. Not derivative, but differential. But it's the same type of deal. And then you can rewrite this as dy is equal to 1 over 2 times the square root of x dx. And that's exactly what they got, except they wrote the dx on top. And it doesn't matter where. Dx over 2 root 2, root x. Okay. Now, I actually, when we get to integration, I really like it this way, but you'll see it this way just about as often. So get used to seeing both of those. They mean the same thing. All right, can I erase that?
And so the dx is something that'll be given in the problem, like it was on the other one. That 0.0.
Okay, when you're using differentials to solve and estimate, yeah, you're given it. When you're doing it for integration, no, it's just a part of the problem. But we'll get there. Okay, I can't explain how it's going to show up until we get there. Almost, it would probably almost be more trouble than worth to try. Okay. Now, all right. How about this one? Take a derivative of that. Y is equal to 2 sin x. What's this derivative?
2 cosine x.
Second? Yeah, dy dx is equal to 2 cosine x, right? Now, there it is. Take the differential of that. All right. The 10 o'clock scholar. Okay, good deal. Glad you're here. Gotta find you. Diamond's here. Okay. And I've told the others as they come in, I apologize for this, but I tried to make out your test yesterday. I could not access the test bank. In the old days, they sent a DVD with everything on it, okay? Now they make you go online to do it, and I could not get that. Their thing was down. We had, I don't know what it was. I just couldn't access it. I couldn't get customer service because they were Eastern time, so we didn't get it.
Is this going to be the last test?
No, well, the last test will be your final exam, and that'll be whatever we cover in chapter 4 if we ever finish 3.9. Okay, what we're doing is differentials now. So take the differential of this. Differential of y is? Differential of y is? dy, okay. And then take the differential of 2x sine x, or 2 sine x. What would that be? 2 cosine x dx. It's like the chain rule, and that's exactly what you got there, okay? So you don't have to take a derivative and then pretend that you're moving the thing over. You just do a dy is equal to 2 sine x dx. Dy is equal to 2 cosine x dx. Just take a differential as you go. But remember, you're chain ruling this part. You're not chain ruling the first part. Okay. Well, you are too. It's dy. Okay. So let's do d. Okay. What's the derivative of that? You may have to work it out. I think you will. Or you can do it maybe in your head. X times negative sine x. Is that what I heard? Okay. The first part. We're doing dy dx. Okay, minus sign. We already did that part. X negative sine x. So it's negative x sine x. So that's just the first half.
You have a plus a cosine x.
Plus cosine x. X cosine x. Because the root of x is 1. So it would be, I would have said it, cosine x minus x sine x. They did it the way you did, minus x sine x plus cosine x. Okay, if you're doing the differential, what was looking at the original, now not this one. Differential of y is? dy is equal to, you do the same thing you just did, negative x sine x plus cosine x in parentheses dx. It's sort of like just a chain rule. Okay? Take the derivative of this and then do your dx. So that's all there is to it. It's not anything all that strikingly different. It's a little bit different, but not bad. Okay, let's do this one. Y is equal to 1 over x. How would you do it? What would be your first step? Rewrite it. And what would that rewrite? Now's your chance. Y to, or x to the negative 1. Okay? So take a derivative of that, dy dx.
1 over x
Okay, you negative 1 over x. Perfect. Okay? And then what would be if you're taking derivative, a differential of that? Differential of y is? Dy is equal to negative 1 over x squared dx. And they wrote the dx on top, which is fine. I sort of like to do it negative 1 over x squared dx. Either way is right. Perfectly fine. All right, they have the little blurb on the side here. Gottfried Wilhelm Leibniz, okay? Both Leibniz and Newton are credited with creating calculus. However, it was Leibniz, okay, who tried to broaden calculus by developing rules and formal notation. He often spent days choosing an appropriate notation for a new concept. Okay? In fact, the dy dx came from him. Okay? I don't know if differentials came from him or not. Why they brought him up here, I don't know. But anyway. All right, let's see. Calculating differentials. Oh, I guess that's what this is. The notation in example 4 is called the Leibniz notation for derivatives and differentials. So he must have been responsible for differentials as well. Named after the German mathematician Gottfried Wilhelm Leibniz. Okay? Differentials can be used to approximate function values. To do this, for the function value given by y is equal to f of x, use the formula f of x plus delta x is approximately f of x plus dy, which is f of x plus y prime delta x. Now, is this just another iteration of what we did before? I believe it is. Okay? Which is derived from this, that your change of y is f of x plus delta x minus f of x. That's approximately the same as your dy. So if you put that in here, here's your f of x plus delta x, plus your f of x. You add that to both sides, dy. All you did here was add this to both sides to get this. Okay? So the key to using this formula is to choose a value for x that makes the calculation easier. Okay? In other words, if you had calculating something at 4.035, okay? Well, let's just do f of 4 plus the change you get from a 0.05. Yeah. And do your dy with that using your f prime. So that's what they're getting at. I assume example 5 was going to show us that. Okay? No, they jumped to example 7. Well, let's do example 5 on this page. We'll come back and do 7. Okay? Example 5. Finding the differential of a composite function, which seems like a brand new thing to do here, but we can do it. Y is equal to f of x is equal to sine 3x. Well, I can't write. Okay, let me try it one more time. Sine of 3x. So that is a composite function. Okay? Now, I don't know why they say find the differential of a composite function when they start by doing a derivative, but we'll do it. F prime of x would then be what? Help me. Okay, you certainly have a cosine of 3x in there. What else? Times 3, chain rule, okay? Now, why they did that step first is beyond me, okay? It seems like to me you could have jumped right to the differential. dy is equal to, forget about f of x, cosine 3x times 3 dx. So I don't know why they did the middle step. If they say find the differential of a composite function, just find it. I mean, why go through the derivative? That's just an extra step. You've taken a derivative, sure, but why have to bother writing it down? Okay? But what they say is f prime of x dx, which is exactly what it is. So that was really not too bad. Let's do example 6. Let's see if we can do it without doing their f of x. If you like putting the f of x in there, do it. But let's just do it this way. Y is equal to x squared plus 1 to the 1/2 power. Okay? What's the differential? Pretty easy. The first part anyway. dy. Okay, good. That's all I was looking for there. Now we do a derivative, and that's what they're saying, writing it out. Just take a derivative of it. What do you get? Second? Okay, you got a 2x there. I'll buy that. Second? Times 1/2. Okay. I'll buy that, so the 2's are going to go out. What else? Second? X squared plus 1 to the negative 1/2, and then you'll have your dx. So if you want to clean it up a little bit, be x over x squared plus 1 to the 1/2 power dx. Or they may write it as x dx over x squared plus 1 to the 1/2 power. Let's see how they write it. Okay? They put a square root in there. I mean, you didn't have a square root to begin with, a radical to begin with, but that's exactly what we got. And this is x dx over the square root of x squared plus 1. Okay. If they don't put it in radical form to begin with, why would you want to put it in radical form at the end? But it's the same thing. Only the thing is, on this time, they wrote it more like this. X over the square root of x squared plus 1 dx. Now, can you imagine this in something like WebAssign? When WebAssign is looking for one form, even though in the book they kept writing the dx up here, then suddenly they put the dx over there. And they'll tell you this is totally wrong. And it isn't. It's perfectly correct. It's perfectly fine. Any one of those four answers is just as good as any of the others. Okay? What's that? Yeah. So, but you don't know whether you got it right or wrong. You assume they told you it was wrong. It was, but it was absolutely right. So, I don't know. Drives me nuts. Okay, as you can tell. Differentials can be, okay, let's see. Yeah. Can be used to approximate function values. To do this for the function, and this is what we just did. I'm sorry. That was the previous one. Let's do example 7 now and see if we can do this. Let me erase what we've got here. Any question on 5 or 6 before I erase it? All right. So use differentials to approximate the square root of 16.5. This is not going to give you the exact, but it's going to give you the approximate. Now let me write down what they had before. F of x plus delta x is approximately equal to f of x plus delta y, or dy, which is equal to f of x plus f prime of x dx. Now, I guess there is a reason to write it all that way, okay? But what they're getting at is let's approximate this thing, okay, by that. Now, in this problem, what is your f function? What is f? It's the square root, okay? The f is, where do I write that? F is equal to, f of x is equal to x to the 1/2 power. It's taking the square root, okay? So what we're doing here is f of 16 plus 0.5. You see? That's what you're doing. Square root of 16.5. 16 plus 0.5. Your x is your 16. Why? That's easy to take the square root of that. Okay? The 0.5, not nearly as easy. Okay? So that's what we're trying to do. The f is the square root function. Now, forget about this middle part. Let's go straight to the last part. Is approximately equal to f of x, okay, where x is equal to 16 and delta x is equal to 0.5, okay? So what is f of x? What's the square root of 16? 4. Plus, now, what we have to do is your f prime. So there was f of x, the square root function. What's f prime of x? You've just done it a couple times for me already. Do it again. 1/2 x to the negative 1/2. Okay? So, this will be, f prime would then be, I'm going to write it this way, 1 over 2 times the square root of 16. Your x is 16, remember? And then you're going to multiply that by your dx, delta x, which is 0.5, right? So this is approximately equal to 4 plus, now, what's the square root of 16 again? Okay. Okay, so this will be 4 plus 1 over 8 times 0.5. Now you can do that on a calculator, you can do it in your head, you can do it anywhere you want to, but what does that give you? $0.625. Okay. Now, while you got your calculator out there, take the square root of 16.5. And this is also going to be approximate.
4.06201.
Not bad, is it? Okay. This is, and we did that without ever taking a square root, though we did use a calculator to calculate simple things. But this is what you got. So 4 decimal places, well, 3 for sure, almost 4, you got exactly the same answer. Okay? So this is a way to approximate it without ever taking a square root. I mean, yeah, you took the square root of 4 twice, but that was easy to do that in your head. Okay. Let's see if that's what they did. I never know if they're going to do it the same way or not. Let's clear this. Can I clear it? Okay. Let's see what they do. Using f of x equals square root of x, we can write f of x plus delta x is f of x plus f prime of x dx. So it would be square root of x plus 1 over 2 times the square root of x, which is exactly what we got, times dx. Remembering what the x's are, okay? The x is 16, and your dx is 0.5. So you have square root is approximately equal to square root of 16 plus 1 over 2 times the square root of 16 times 0.5. That's exactly what we had. 4 plus 1 over 8 times 1/2. They wrote it that way. So it's 4 plus 1/16, which is another way of doing it. That's exactly what you got. 4.0625. Whereas the real value is that's the approximate value. Oh, they didn't show it. In the book they did, I think. No, they didn't. I thought they did. Yeah, they did. Yeah. The approximate value is 4.0620. So not bad at all. All right. Now, the tangent line to approximate the square root of 16, the square root of x at 16, square root of 16 is 4. So that's the place we're starting. We're going to approximate it at 16.5. And you see this is a pretty small scale. That would be 18 right there. That would be 17 there, 16.5 is right there. Not far off at all. And this function is the 1/8 x plus 2. Where did they get the 2? Okay. The tangent line approximation to f of x equals square root of x at x equals 16 is the line g is equal to 1/8 x plus 2. Now, let's go back and remind ourselves why that's the case. Okay? Remember, f prime of x is equal to 1 over 2 times the square root of x, right? That's what we did before. And when you plug in okay, that's your derivative, and your g, why do they go to g of x? I guess is differentiate. You evaluate this at f prime at 16 would be 1 over 2 times 4, which would be 1 over 8. So that's where your 1/8 comes in. So your g of x, your linear approximation, would be 1/8 x, and then where is that 2 coming from? Okay, well, seems like to me it's x minus. I can tell, sure enough, that is coming in the right direction here, but why? Oh. Here's why. They skipped a step here. Yeah. This is 1/8, that's your derivative, times x minus 16. That's where it's coming from. So that would be 1/8 x minus 2. That's where, whoa. Why isn't it? It's a plus 2. Why is it a plus? Oh, yeah, the delta, okay. That seems like it's always minus. That's where it's coming from. I'm not going to get in. They just told you that is the tangent line approximation to it. You can go back and do the math, but that's pretty much where it's coming from. Okay. Whoa. Are we through? Yes, we are. 3.9. Finally finished. Okay. Do any of the odds 5 through 9? They're all at calcchat.com. 7's at calcview.com. Do 11. It's at calcchat. Do 13 through any of the odds 13 to 17. They're all at calcchat. 13's at calcview. Do any of the odds 19 to 27. They're all at calcchat. 23 is at CalcView. Do 29 is at CalcChat. Do 31 is at CalcChat. Okay? Then do any of the odds 33 through 41. I'll let you choose which ones of those you do. They're all at CalcChat. Then do either 43 or 45. They're both at CalcChat. 43 is at CalcView. You can think through 47. It's pretty relevant to what we were doing. You can look at the true-false 49 or any of the odds 49 to 53. I really don't like true-false. I don't like you reading something in a book that may be false. I mean, I just don't like that concept. But it's good to think through. Now, review exercises. These would be good to get ready for the test. Any of the odds 1 through 7. I think they're all at CalcChat. Yep. Either 9 or 11, they're at CalcChat. Any of the odds 13 through 17, they're at CalcChat. 19 would be at CalcChat. Any of the odds 21 to 25, they're at CalcChat. Any of the odds 27 to 33, they're at CalcChat. Do 35 is at CalcChat. 37 to 41, they're at CalcChat. 43 or 40, no, any of the odds 43 to 47, they're at CalcChat. Do 49, it's the only one like that. And then you can look at 51 is a writing thing, but you can read through that and think about it. 53 is a modeling data. You can do that if you like. Finding the limit, any of the odds 55 to 63. Do either 65 or 67. Everything's a calc chat, and 69 through 77. Then there's some word problems, 79 through 87. And then using Newton's method, 89 or 81, or 91, sorry. Then there's a 93, a 95, a 97, and a 99, and a 101. So any of those. There's some problem solving there. If you're really into that, it looks like some fun things, only if you're interested in it. And let's see. Do we have time to get a little bit started on integration?
5 minutes.
5 minutes. I think we do. So let's get out of here, there, discard here, and close this, and go to 4.1. Okay. Sorry I don't have your test ready in Chapter 3. I'll try to have it ready by Monday. But now we're going to start the integration part, which you'll see follows very directly from differentials. You won't see it right away, but you'll see it does get there. Okay? We'll start from the current slide. So integration. Why they put it in Cal 1? Well, number one, you run out of stuff to do, so we go to this. But we first think of it in terms of antiderivatives. Okay? We just did derivatives. We now are going to inverse that. It's just like back in grammar school. You learn to add, right? And finally, when you finally got all those addition things in your brain, they turn around and made you undo it with subtraction. And then they had all the flashcards and everything with multiplication. You had to learn a whole bunch of other things, and then they turned around and made you undo it with division. And at some point, you learned to raise things to powers, and then probably a few years later, you learned to take square roots or roots. You know, everything you do in math is a yin and a yang. You know, you do something, then you undo it. Well, we've been taking derivatives out of the ears, and now we're going to do the inverse of that, antiderivative. But even in functions, remember, we did functions, and then we did inverse functions. You took sines, and you did inverse sines. You know, in everything, you go turn around and do the opposite of it. So now we're going to be doing antiderivatives, and that will lead to what we call indefinite integration. So our objectives here are to write the general solution for of a differential equation, which is rather bizarre because that's another course, you know, and use indefinite integration notation for antiderivatives. Okay. We use basic integration rules to find antiderivatives, okay, and we will find a particular solution of a differential equation, which seems bizarre to be doing in a calculus course rather than a differential equation course, but they're certainly related. So, antiderivatives. This is their standard notation. I never have really liked it, but it's fine. To find a function capital F whose derivative is little f, and the little f is 3x squared. We want some capital F that this is the derivative of capital F. In other words, capital F prime is equal to little f. You might use your knowledge of derivatives. I think you could right off the top, couldn't you? What would be the function capital F?
X cubed.
X cubed, exactly. So capital F would be x cubed because the derivative of x cubed would be 3x squared. Exactly. So the function capital F is the antiderivative of f. Guess what? That's what integration is. Taking antiderivatives, finding those antiderivatives. So the definition of an antiderivative, the function capital F is an antiderivative of f on some interval I when f prime of x is equal to f of x. Capital F prime of x equal to little f of x for all the x's in that interval I. Now that kind of looks like a 1, but that is an I there. It doesn't look as much like an I there, but that's an I. I don't know why it looks that way. In the book, it's much clearer. Okay. Note that capital F is the antiderivative of F rather than the... Does that make any sense at all? No, I'm sorry. I left off my article. Note that F is called an antiderivative of F rather than the antiderivative of F. I may have just misstated it, okay? And here's why. We've already said that F equal x cubed was an antiderivative of our 3x cubed, right? But what if you had x cubed minus 5? What's its derivative?
3x.
Squared again. So it's not the only antiderivative of your little f, it's just one of an infinite number. Okay? X cubed plus 97. Its derivative is 3x squared. X squared minus 4/3 pi to the 7th power. Just a number, its derivative would be 3x squared. Okay? All these are derivatives of 3x. They said that wrong. They're antiderivatives of 3x, f of x equals 3x squared. In fact, for any constant capital C, why they did capital C, I'm not sure, the function f of x equals x cubed plus c is an antiderivative. Now, it has to be a constant. You can't have a variable in it. It has to be a constant. So here's how we represent antiderivatives. If f is an antiderivative of f on some interval I, then g is an antiderivative of f on the interval. There they did it again. I, if and only if g is of the form g of x equal capital F of x plus c for all x's in I. That was a little clearer, where c is any constant. Any constant. As big, as small, any constant you might want it to be. Okay? All right, I think we did finish. Okay? We will... Whoa, that's not my pencil. There's my pencil. All right, you didn't get far enough for this, for any homework here. We did do Theorem 4.1, didn't we? Yeah. There is a little proof there. You can do that if you want to. We're starting at the top of page 249. I sure hope I can get your test done before Monday. I have that ready for you, hopefully.
Yes, sir.
I was hopeful to have it today, but couldn't get it. All right. We'll be through with this.